All right, today we're going to look at a chemical reaction that honestly looks like pure magic. We're talking about a liquid that changes color just like a traffic light, all with a simple shake. But as you're about to see, the real magic here, it's all chemistry. So, picture this. You've got a bottle with a yellow liquid inside. You give it a little shake, and boom, it turns red. Shake it a bit harder, and it goes green. But here's the really wild part. You just set it down, and on its own, it slowly fades back to red, and then all the way back to yellow. How on earth is that possible? Well, to unpack this mystery, we gotta start with the ingredients. And you might be surprised to find out that this whole incredible reaction comes from just a handful of really simple, everyday components. And that's it, seriously. Just water, glucose, simple sugar, sodium hydroxide, which is basically drain cleaner, and this special blue dye called indigo carmine. And let me tell you, that dye, that's the real star of the show. See, indigo carmine is what's known as an indicator, which means its color isn't just one thing. It can change. And it changes based on two very specific conditions: the pH of the solution around it and its oxidation state, which is just a fancy way of saying whether it's gained or lost some electrons. So let's get into the first secret here, pH. This is where that sodium hydroxide, the drain cleaner, comes into play. It completely changes the chemical environment and sets the stage for everything that follows. Okay, so here's the deal with indigo carmine. It has this critical tipping point at a pH of about 11.4. Below that, it's blue. But when we add the sodium hydroxide, it makes the solution super basic, pushing the pH way above 11.4. And this forces the dye to change its structure. And in this new form, it actually appears yellow. So you might be thinking, wait, where does the green come from? Well, it's not some new chemical. It's actually just our eyes mixing the colors. You have some of the dye that's still blue and some that's now yellow. And when you see them together, your brain reads it as green. It's kind of like mixing paint, but we're doing it with molecules. All right, now for the second, and I'd say most important secret. It's a process called oxidation reduction, or just redox for short. The best way to think about this is like a constant chemical battle, a tug of war over electrons. And this battle is what drives all those traffic light colors. So here are the two players in our battle. On one side, you have the glucose, the sugar. It acts as a reducing agent, which means it gives electrons to the dye. This pushes the color toward yellow. On the other side, you've got oxygen from the air. It's an oxidizing agent, so it does the opposite. It takes electrons from the dye, which shifts the color back toward green. So when you just let the bottle sit there, not much oxygen can get into the water. That means the sugar has pretty much no competition. It just keeps on giving its electrons to the dye, reducing it more and more, until the whole solution settles into that stable yellow state. In this round, the sugar totally wins. But then you shake the bottle. Now, the shaking itself isn't the magic trick. It's just a really good way to mix the oxygen from the air that's trapped in the bottle into the liquid. This sudden flood of oxygen comes in and just rips electrons away from the dye, completely overpowering what the sugar was doing. The dye gets oxidized, and the color instantly flips to red, and then green. This time, oxygen wins, hands down. Okay, so we have our two big secrets. pH sets the stage with the right colors, and that redox battle is what makes them change. So now, let's put it all together and walk through the entire traffic light cycle from start to finish. Here's how it all plays out. When the bottle sits, the sugar reduces the dye, and it turns yellow. A gentle shake adds just a little bit of oxygen, which partially oxidizes it to an intermediate red color. Then, a really vigorous shake adds a ton of oxygen, fully oxidizing it to green. And then, as soon as you stop, the sugar goes right back to work, reducing the dye again, and the whole cycle just reverses itself. Pretty cool, right? So, when you boil it all down, the whole thing is really just a battle between oxidation and reduction. It's not a one-way process. It's this dynamic, ongoing competition. The color you see at any moment, that's just a visual scorecard for who's winning that battle. Now, for some fun, what happens if we start tinkering with the formula? A great way to really check if we understand something is to change one of the ingredients. So, what if we swap out that strong drain cleaner for a much weaker base? Okay, so using a weaker base like sodium carbonate instead of sodium hydroxide has massive consequences. First, the pH drops to around 8 or 9. That's way below that critical 11.4 number. This also makes the reaction painfully slow. In fact, you have to heat it up just to get it to go at all. But here's the biggest change of all. Because the pH is too low, the dye never turns yellow in the first place. It starts out blue, and it stays blue. This means that redox battle between the sugar and the oxygen now creates a totally different spectrum of colors. It just goes to show how critical every single ingredient is. So what are the big takeaways here? Well, first, what looks like magic is really just a cool chemical battle over electrons. Second, that special dye changes its color based on two things: its environment, the pH, and its oxidation state. Third, the magic of shaking is just a way to add a key player to the game: oxygen. And finally, as we just saw, chemistry can be super sensitive. Change just one ingredient and you can get a completely different result. You know, this simple little bottle of chemicals really points to a much bigger idea. So many things throughout history that seemed magical were just science we hadn't figured out yet. It kind of leaves you with a final question, doesn't it? What other magic is out there in the world just waiting for the right scientific explanation?